Okay, our first talk is given by H.Song and Professor Daniel from Stanford University. Professor Daniel is a professor at Stanford Institute for Computational Mathematics and Engineering, and also Department of Energy Resources Engineering. Before joining Stanford, he was a professor at University of California, San Diego. His current research is about environmental fluid mechanics, applied and computational mathematics, biomedical modeling, etc. Our another speaker for the first talk is H.Song, who is a PhD student in energy resources engineering from Stanford. His background includes a master's degree in petroleum engineering, a bachelor degree in civil and environmental engineering, and also an industry experience as a petroleum engineer for 3 years before joining the Stanford University. His research focuses on data-driven methods and to understand the governing mechanism of data. Their talk today is about transfer learning on multi-fidelity data. So without further ado, let's welcome our two speakers for the first talk. Daniel, you may take over.
So I'm not able to share the screen. If
you
let
me make you the
for now, right? And then Dong will take over with his slides.
Yeah, I think you can share.
Okay, now yes, okay. Wait, which one? Okay, this one. All right. Well, so first of all, thank you for the introduction, and let me see if I do full screen. Yeah. So that's better. So the first sort of introductory part of our joint talk with Song is intended to be slightly provocative. I would like to get your feedback and opinion on that. So I would, my personal perspective that is certainly not shared by many of my students is that there is the link between neural networks and machine learning in general and scientific computing is not straightforward or obvious, because machine learning, like statistics, thrives on big data, on availability of unlimited supply of data, high quality data. But in systems that we care about most in other engineering or natural, we have the opposite problem. We have very often very limited data. The data that we have are noisy and error prone. And more important than not, it's very often not representative of the population as a whole. And so making inference on such data is notoriously hard. And so that raises the question, how are neural networks used in scientific computing? And of course, in your group, they are used very successfully in many ways, but sort of three large classes that I could identify, and I'm happy to be corrected, is one is a post-processor of data. And that's where I believe neural networks really shine as an image classifier and to find the patterns in data. But I want to focus on two other uses of neural networks. One is as a solver of a partial differential equation, and the second or third on my list is as an emulator or surrogate of PDE-based models that would be used in, say, ensemble-based computations. So if you think of the use of neural networks as a solver of a single PDE, or a single solve of a given PDE, then what do we usually expect from PDE solvers? Well, we expect one of two things, ideally both. We want them to be more accurate or stable than the existing alternatives, or at least we want them to be faster than existing alternatives. So if you look at performance of neural networks as solvers, what we usually have is this root mean square error that you have here. It comes actually from Dong's talk, but it's something that I see repeatedly in papers. So the error is on the order 1, it's or 10 to the minus 1. It's not an error that we would accept from any other numerical solver. So much more work needs to be done to make that, competitive with existing finite elements. And then clearly, if you account for the training and parameter tuning and things like that, in terms of computational effort, it's not competitive very often with, say finite element solver. So then, what's I would argue that where neural networks really shine is when we use them as surrogates for ensemble-based computations. And that's because once you train them, then the cost of running additional realizations is really negligible. And then it suggests they use in all these areas of scientific computing where we need to generate multiple realizations. So that could be uncertainty quantification, data assimilation, inverse modeling, optimization, and all things like that. But then the practical question that we are trying to address in our group is how do we use them for practical problems or large problems of scientific computing? And the issue is, can we train neural networks at a smaller cost than the cost of ensemble-based computations? And this is my last slide, and then I'll give the floor to Dong. So to answer this question then of relative benefits of neural networks versus just straightforward ensemble-based computation. So we need to understand where the data come from. In scientific computing, it almost never comes from observations. And in fact, you could not really generate enough data, say in material science you don't have enough samples to train a neural network, most often than not. So we have to rely on simulation data. And the simulation data usually come in the form of output of forward runs of a PD-based solver. And so then, even if you ignore the training costs, we have to acknowledge that we need a large number of forward runs of a PD-based model to generate this data. So let's say it's S1. And then ensemble-based computation relied on the same thing, essentially, that they generate enough, they do the same thing, they run forward models. So then the cost, the problem is that very often the number of realizations that you need to train a neural network and the number of realizations you need to, say, conduct ensemble-based computation is comparable. And then the path forward that we see is, how do we reduce the cost of generating data for ensemble for neural network training? And there are several approaches to this goal. One is the use of genes, which is our Bayesian nets, and something that is a topic for another presentation. I think Marcos Katsoulakis, Professor Marcos Katsoulakis is here, and that's why I didn't want to talk about that at this meeting. Well, I didn't know that Marcos would be here, but I want to advertise this, also talking to George. I think I would love to expose you and give a talk on this topic. I think it's worthwhile doing. But today we will talk about, by we I mean Dong, we'll talk of another way of reducing the cost, and that's using multi-fidelity data for neural network training. So with this, I will stop, and Dong, please take over.
All right. Well, thanks for that, Daniel. Can I share the screen? Yes, I can. Can everybody see the presentation? Thumbs up, thumbs down?
Yes, yes.
Yeah,
Everything's
yeah,
good.
some are
Good, yeah.
Okay, well, my name's H.Song, and I'm a PhD student at Stanford University. And as Daniel just said, I will be talking about using transfer learning on multiple fidelity data to train a surrogate model at a low data cost. So I will admit this person. So I'll talk about the motivation behind this project, which actually I think Daniel covered, so I'll go through that pretty quickly. Some background information relevant, especially a little bit about transfer learning itself. And then give you guys a feel for the actual problem we solved, our multi-phase flow problem, and how we split that problem into a data set that we can train upon. And then go into details about the methodology that we use to train the network, how we used multiple scales of data into a workflow to train the model, and share some results and some conclusions from that results. And since this project is a still going thing, talk about some improvements we've made since the paper was written. And so just briefly, much along the lines of what Daniel just said, you know, we want to justify why uncertainty quantification is important. And so how do we make decisions, right? It's if we know the ins and outs of everything that's going to happen that we're making the decision on, then we don't need UQ. But thankfully for us, there's uncertainty in the world. So when we have uncertainty, you know, we can do things with it. We can calculate expected values. We can slap a factor of safety or a utility function to make decisions. But how do we determine this uncertainty becomes an important question. And so, and this is, I think, the heart of UQ, like determining uncertainty to base decisions off of is not easy. And there's many ways about this, but I think the golden standard is Monte Carlo simulations. And typically, so we will need a input distribution, a model that can process the inputs to outputs, and then we would get an output distribution. And the way we go about Monte Carlo is we do this many, many times. And then we can end up with a distribution, and we can make decisions based on a distribution. We get, like going back up the steps, we can get the expected values, we can have a utility function, and can make the decision. And there's usually a cost associated with this forward pass of this model. And by model, I'm talking about typically a PDE-based model, a computational solver, but it doesn't necessarily, like, and this idea of cost doesn't have to necessarily be in a model. It can be also getting data. There's a cost associated with this. So decision-making can be an expensive process, and we want to reduce the cost of decision-making. There we go. So one way to reduce the cost is reduce the cost of these forward passes. And one way to do that is neural network surrogate models. And this is becoming a very popular field of research, as your group is obviously very well into this field. But the pros are it has very fast runtime. So once the model is trained, it's very fast. So as Daniel said, it's very applicable towards applications where you need many, many forward passes. And also it's pretty flexible. So a network can be manipulated into many different problems and tasks. And transfer learning is a great way of doing this. And one of the cons traditionally is it needs a lot of data, and especially it needs even more data to be general, which means So a neural network model will perform very well on the training data set, but oftentimes it will do very poorly on the test data set because the model has not become general. And also, if we can think of a solution space, a neural network model typically does very well interpolating. So for interpolation tasks, but if it is seeing a test data that it's never seen before, that is outside the realm of the space of the information it was previously given, it can also do quite poorly. And so I think it's very well established that if you have enough data, a big enough network, and if you have the right set of hyperparameters, neural networks can emulate most everything. But usually we don't have any of those three, so we need some tricks to make our neural network surrogate modeling possible. And just the typical workflow for a neural network, you have to do something with the data. You have to pick and develop a model, and then you have to train the model, and then you apply the model. So a lot of work, it seems, goes into, so we have a lot of methods to solve PDEs and other computational solving, and we take inspiration from those types of fields and then bring it back into these neural network training schemes. And that's how we can reduce the cost or make these workflows more valuable. So like some notable ones would be work by Rossi, adding new data points to address shock type problems, and a lot of work by your group. So to get into transfer learning, this is a very, I guess, popular example where a neural network will do an image classification of a dog or a cat. So we have an image and we're looking for if it's a dog or cat. And it seems that for a neural network, the closer it is to the input, it's processing very generic information. So for an image, we can think of, it'll detect lines and how the lines are connected, maybe a circle. And then near the end, it does more of the task itself, like actually classifying and giving a percentage to if it's a dog or a cat. So what transfer learning does is we keep the generic section that might, look at the image as just a collection of lines and points, and then it can change the classification task. So we can give it a picture of a car. So say this model was trained on many pictures of dogs and many pictures of cats, and then we have a few pictures of cars and boats, and hopefully we can train it if we can keep the bulk of the model. And for image processing tasks, actually transfer learning has become it's the norm as opposed to the exception. If you look at challenges like ImageNet, the last many champion models have been trained using transfer learning. And some other comments about simulators and convolutional layers and encoder-decoder setups, which so an encoder-decoder setup with a convolutional layer was my model of choice. So a simulator goes through 3 very broad strokes. So you take a PD model and then you discretize it, and then you turn that into a system of algebraic equations, and then you solve the system. And the way we develop the system of algebraic equation is we have a grid, or at least for the finite volume, or we have a grid, and we look at the so say we're interested in the center cell, and we look at the cells around it, and we develop some relationships, and that will be our system of equations. And a convolutional layer, it actually looks at a group of so a group of pixels in our case, and it will do a calculation. So for our purposes, it has a weight and an activation function. And so it will scan through the image and then form a new, I guess, a latent image to work with in the next layers. And for the encoder-decoder setup, the important part is that we start with a large latent image, and then we end up with a small latent image in the middle, and then we take that information and build it back out. So a key thing is that in the middle that there is a relatively few amount of latent variables. And the hope here is that when we're replacing a simulation workflow, that the latent space would reflect something of the state variables. And also because in the encoding part where actually it's convolutional layer upon convolutional layers, each convolution or each latent variable in the middle has seen a lot of the image. So, and this is kind of a brief schematic of the network I was using. So in the input, I have a 128 by 128 image, which is the permeability map. And the encoding layers, after the first encoding layer, we're at 64 by 64, second encoding layer 32 by 32, and then we decode back out. And specifically, it looks like this, where exactly, it's same as the picture before. We have the permeability field, which is the input. And then we have our first convolution, first dense block encoding, convolution 2, dense block convolution transpose, dense block decoding, and convolution transpose. And we have our output. And these are the dimensions. And this network was actually originally found in the work of Mo and Zabaris. And we just happened to like it and that it worked, and we built our method upon it. And also a motivator for using multiple scales is this accuracy scale trade-off. So whenever a simulation model is smaller, it runs much faster, but it can be less accurate. So whenever I do an 8x8 model, it's quite inaccurate. So I'm measuring breakthrough time, and this is we're assuming a uniform permeability map for this just very simple example. But as the model becomes more and more sophisticated, larger, we kind of asymptotically approach a solution that's hopefully closer to the ground truth. So this is our actual problem. And this is a multi-phase flow problem where we have our PDE and our Darcy's law. And we use the black oil formulation to discretize this. And some important assumptions here. We only have water and oil phases, and they are immiscible. And we have some boundary conditions. So we have no flow boundaries up at the top and the bottom. And we have constant head on the left and the right, but the left head is a little higher. So there's a flow from left to the right. And the concentration of each phase. So on the left, phase 1 is at concentration 1. And initially, the entire field is filled with phase 2. So the concentration of phase 1 initially is 0. So you can think of it as like a water flood. If you guys are in the oil and gas field, a water flood that's sweeping the field from left to right. Or if you're environmental person, maybe a contaminant is flowing through a aquifer. And this is some realization. So the hotter it is, the higher concentration of S1. So and this is like at the end of year 0. And so until at the end of year 15. So we can see that the front is traveling from left to right. So how we pack this into a data set is we, for our X's, we always have a permeability map in high fidelity scale, which is 128 by 128. And to get our multiple fidelity data, we naively just run it through our simulator to get the high fidelity simulation results. But to get the low fidelity simulation results, we must upscale this permeability map into a tensor. And so we upscale it based on if it is in the direction perpendicular to the flow, we do the weight at distance weighted arithmetic mean, and in the direction of the flow, we do distance weighted harmonic mean. And so the inputs are always this 128 by 128 permeability map, but for the outputs, we can have 2 different scales. So going into the actual methodology, so we have split up this training scheme into 3 sections where phase 1, we work with the low fidelity data. Phase 2 and 3, we work with the high fidelity data, and we'll go into each phase into more detail. And just so we can keep in mind, the blue blocks indicate a untrained network block, green indicates a trained network block, checkered means it's a semi-trained network block, and gray indicates a locked block where the block does not accept gradient updates. So in phase 1, we will first initialize the full model. So the full model should take the high fidelity inputs and high fidelity outputs. But in step 2, we're going to remove the high fidelity output block, and we're going to temporarily replace it with a block that matches the output size of the low fidelity data. So this is where our transfer learning is starting to take place. And then we will train this modified network, which takes the high fidelity inputs and low fidelity outputs using the low fidelity data, because again, our inputs are always in high fidelity. It's the not upscaled permeability map. So once we have the network trained on the low fidelity data, we will replace the temporary layer back with the original output layer. And then we will disable the gradient updating for the first 4 blocks, that we've already trained. And then we will train just the final layer on high fidelity data. And this is really where the transfer learning takes place. But I found that sometimes this is not quite good enough. And so we've added a phase 3, where we enable the training of all layers, and we train it again we let the entire model see the high fidelity data again, but I found that it works best with very small learning rates. So we can think of this phase as fine-tuning the neural network. And so I also did a hyperparameter search, but actually one of the findings of this study was that for similar problems, actually, much like we can use transfer learning, we can recycle hyperparameters. So Daniel's previous student, H.Song, has worked on a similar problem, and I was able to mostly recycle her hyperparameters. I explored the spaces near this hyperparameter, and it did not change very much. And also, I would like to add, I know Daniel used this slide or this graphic as a example for very high errors associated with these models, but actually, so this hyperparameter search was done using a very small subset of the data. The the network only saw a very small subset of the fine data to perform the hyperparameter search, which actually worked well for the larger data sets as well. And the hyperparameters I iterated between were the learning rate, the weight decay, the factor, and minimum learning rate. And the optimizer I used for my training was Atom. So once we trained the neural network, so we expected to be able to.
Dong, I have a question for you. Why the errors are so big? Why 20%? These are relative errors?
No. So this is, so we'll see in my final result that the errors are about and more than order of magnitude smaller than these.
But what are these? RMSC, is it relative or is just?
So this is root mean square error during the hyperparameter search, and the hyperparameter search was conducted with a very small subset of data. About I want to say I think I used 1 hour's worth of data for the hyperparameter search.
Okay. Yeah.
Yeah. So we just wanted to show that a small subset of the data can be used for hyperparameter search, because I mean, our method would be much less valuable if we need a ton of data to do the hyperparameter search, and we need less data to train the actual model. And if you guys have any questions, feel free to stop and ask, just like George just did, or Dr. Karniadakis. So yeah, so once we train the model, we expect to see the model mimicking the simulator. So the permeability map is on the top, and the differences between the model and the test data is displayed on the bottom. And we can see it mimicking the test data quite well. We can see the evolution in time, the front. And there's some differences up at the front, but I think it's acceptable. But we should also do a sanity check, right? Because at the end of the day, it's just squiggly lines that are propagating from left to right. So a test we did was to give it a homogeneous permeability field and see if it can propagate a straight front from left to right. And it could. So this was a good sanity check to see if our model was learning a general thing, and it was. So again, test data for a homogeneous front or homogeneous permeability field, we expect to see a piston-like displacement, and yeah, that's what the network is predicting. And so this is just a show of I guess model performance throughout the time steps, and it does really well in the early time steps and breaks down just a little bit near the end, but for the purposes of uncertainty quantification, it was okay. So here is some performances. So there's a lot on this slide, and if anything is unclear, please ask questions. But so we first did a benchmark test. So we had the neural network, and we just trained it on many just high fidelity data, which is the blue line, and just low fidelity data, which is the red line. And on the x-axis, we have expressed it in data generation budget and compared to root mean square error. And so we can see on the low fidelity model, it reaches an asymptote, and we think that it's related to the discretization error of the low fidelity model, because I've tried adding many more data points and it did not improve. And also each of these data points are derived from, I think, 10 training runs. So it's got some, the standard deviation expressed in the error bars. And for the high fidelity data, we did not see the limits of it, but for the uncertainty quantification tasks, somewhere between 60 and 79 hours, we were able to develop a good enough model to perform that task. And so to express our goal of training a surrogate model for a cheaper data cost, we essentially want to be below these two curves on the left side. So we want a cheap data or data cost efficient model that performs well. And so this is the what we ended up with, which is actually this point right here on the right-hand side. So on the right-hand side plot, we have the root mean square error and the number of high fidelity data in the training set. So this square data point, which extends this line, is here. So all of these black data points were trained using a various mixture of 12 hours of data, 12 hours of data budget. So like this point would be 25 high fidelity simulations and 1,015 low fidelity simulations. And the optimum point was 100 high fidelity simulations and 573 low fidelity data simulations. And with just 12 hours of multi-fidelity data, we're able to get somewhere along the lines of 79 hours of high fidelity only data. So this is pretty great. But it's not a real test of how it would perform at a uncertainty quantification task. So on the next slide, we have actually built the distributions based on the breakthrough times. So we looked at the breakthrough times of various amounts of high fidelity models, high fidelity simulations, low fidelity simulations, and the model. And the model and the high fidelity simulations, as you can see, are pretty much on top of each other, whereas the low fidelity simulation deviates from those two lines. And that's, again, attributed to the numerical errors associated with a coarser grid.
Can you tell us what breakthrough time is, please?
Yes. So a breakthrough time is, so we have a front that is traveling from left to right, and we're seeing when this front meets a point in the, so I set the goal mark at the 100-meter mark for this exercise. So when the saturation at the 100-meter mark changes from 0 to, I think, 0.1 or above some threshold value, I count that as it has met the threshold, and that is one data point.
Got it.
Build that CDF.
Thank you.
Yeah, great question. So yeah, and then again, and in the zoom out view, we can see that I've built the same CDF using various amounts of high fidelity simulation data. And again, when we have fewer data, our simulation or our CDF does not converge. And we took the high fidelity simulation at 292 hours as our ground truth, because after that, the CDF did not change very much. And so,
excuse me, quick question. Yeah. This is Panos Tinis from PNNL. So how much time did it take to train your approach? What you call the model, I suppose, right? The black line.
Yeah. So it takes about 3 hours for a somewhat robust training. And I'll get into the pros and cons of this method. And I guess one of the ways I made this method more robust is that each phase I gave it 4 1 second. So I gave it 4 times to initialize, and I chose the champion model. So at each phase, I let it do it 4 times, and the best one moved on to the next phase. But if we can reduce, and 4 was pretty robust. But if you can be, if you're really in a hurt for time, then you can reduce that amount and train it faster, but it may be less robust.
So the low fidelity training was 24 hours, right? And the
No, 3 hours total for this entire process.
No. I'm talking about the low fidelity, the one that you have there, where you say 24 hours in the figure with the breakthrough time. There is a 24-hour next to low fidelity.
So I am not being very clear here. So the model was trained using 12 hours of data, and these curves are generated using just the simulation. So this is comparing my model to the traditional Monte Carlo way of getting distributions.
Yeah. So what I'm trying to understand here is the difference between, at least, on the eyeball norm, between the low fidelity and high fidelity is not very large.
Mm-hmm.
So I'm trying to understand how much effort does it take to go between the low fidelity and the multi-fidelity, and if it's worth the time,
right,
for this kind of small.
Is it worth it? I think that's.
Yes.
I think everybody's asking that. Is it worth it?
Is it worth it? Because the improvement, at least in the eyeball norm, is not very large. That's all but I don't understand exactly all the numbers that appear here. So maybe I'm asking the wrong question.
Well, so I guess if it's worth it depends on your application, right? So if we're
we also have Wasserstein metric and distance and KL metric, right? So it's not just what we have a visual one.
So I mean, visually it may seem close, and I guess the interpretation of the CDF, how valuable it might be, depends on your application. But whenever we compare it to metrics which we can compare different distributions with, like such as KL divergence and Wasserstein distance, we can actually see that our model is very close to the ground truth, and it is, especially in the form of KL divergence, the distribution is actually a little different than what our ground truth is.
But also, I think, George, I think that the point here is, even if multi-fidelity data are useless, just use coarse data, right? That's whatever speeds up the neural networks training.
So for the KL divergence, I see that the high fidelity KL divergence is larger than the low fidelity one.
So whenever we have very few data points, so this is again in terms of data budget. So
okay,
go for it.
So these hours that you have, these numbers of hours, is how much somehow translates to how much data you're using, right?
Yeah. So you have about
to generate the data. Yeah. It's a good. Actually, it's a good way to see it. I agree with Daniel. It's because that was the last bullet of Daniel had there. It's like, somebody has to generate this data. Don't hide the cost. So here they have it. I think I like the Wasserstein distance the most. It tells you that actually you get a good answer with comparable to 72 hours of high fidelity data. That's bottom line.
Mm-hmm.
Yeah.
Mm-hmm. Right.
Okay. Thank you.
Oh no, great question. Yeah, and
hello, this is Lulu from Europe. I have a similar question. So it seems to me your low fidelity is already good enough or not good enough. It's okay. Have you tried even lower fidelity? Let's say even worse fidelity.
So actually, that is a thing I am working with right now, is incorporating 3, or I guess like n number of steps. So it would add, more phases and even more multi-levels of data to train this neural network. And it's looking pretty promising. And actually, whenever we have, so I've built this plot with a 32 by 32, and 32 by 32, actually the difference is significant, but it actually still helps the training.
Okay, thank you.
Great question. So from this study, we reached 4 major conclusions. The CNN surrogate models trained on multiple fidelity data can reproduce outputs on the fine scale, which is great. Training on multiple fidelity data reduces the data generation budget about 7-fold, as we saw in the 2 slides ago, compared to just training on high fidelity simulations alone. And for a data generation budget of 12 hours, the CNN trained on multi-fidelity data exhibits a smaller error metric on the test data compared to CNNs trained on exclusively on high fidelity or low fidelity simulations. And the CNN trained on multiple fidelity data seems to be insensitive to the discretization error of the low fidelity simulation once it's been trained by the high fidelity in phases 2 and 3. And so this is a ongoing thing, and we've reduced the data cost by about 25% by modifying the loss function. And again, I mentioned that we needed to do multiple iterations at each phase to make this method more robust, and the loss function modification seems to have made it more robust, and I'm seeing how much of that I can reduce, and that would result in a reduced training time. And also we're trying to approach this type of workflow to other problems. And with that, here's some references I talked about or meant to talk about in this talk, and any other questions?
And can you stay with the references because there's a delay? So
yeah, so the first one was, that's the, I guess, reference for the transfer learning itself. The second one's the upscaling method, and the second 2 are papers I actually took a lot of inspiration from, and the third one is this paper itself, or the last one is the paper itself.
Right, that's the one that I saw and invited you, right? I have a question on
yeah.
CNN. Actually, 2 questions. One is, did you try to put noise in your testing data, like 5% noise, to see? Because basically you're learning like a map, and I'm not sure actually if you're learning a stable map. So did you try to put some noise in your testing data and see like a 5% noise results in an extra 5% error or in 100% error?
I have not, but that's interesting suggestion.
Yeah, we like to do that these days because you could be surprised sometimes, and of course, since you are dealing with real applications, that the other question, why you use a CNN? Because in this type of applications, you're not going to have nice square lattices, data sitting on lattices, and so on. It's like I think you're talking about reservoirs, right, which are very complicated geometries and so on. A DeepNet would do that and would do very well, but I was wondering what's the motivation behind the CNN to do it fast?
So the CNN, I mean, the motivation is it kind of resembles a reservoir simulator workflow, but actually in the next step section, I mentioned that we're working with different applications, and we're working with a flood data set, which is actually a unstructured mesh.
Right.
And so you are not using CNN there, right?
No, I'm actually using a DNN with some other tricks. So a fully connected neural network. And also, I think to address your first problem with the noise, so yeah, our sanity check there was giving it a homogeneous permeability map that it's never seen before to see if it can replicate the piston-like displacement.
Any other questions for Tom or Daniel?
I have a question about one of your introductory slides. I think it was.
Can you please say your name? Say your name.
Yes, Shervin Parsi.
Yes, sir.
Yes, I think it was slide 6 or 7.
6.
Oh, 7 maybe. Yes. So here you separate your neural network to 2 parts, right?
Sure.
And are you so you said that the first part, the second part has more information about the label, and the first part has more information about input. Am I understanding this correctly?
Yes. So I tried to find the reference for this, but I could not. It was just in the class notes, and it just seems to be a thing everybody accepts, but I could not find a reference.
So yeah, because this is so because if you see the deep neural network as a Markov chain, that each layer is a random variable that gets its input from the previous layer, the data processing inequality tells us that the first layer is always more informative about both X and labels than the last layer. So the first layer is always know more about both label and X, your input, your image. And I know it's appealing to say that this is the last layer who does the classification, because that's where you read the dog and cat, but that violates the data processing inequality. So I don't know, where did you use this? And I want to say that the advantage of deep neural network or many layers is computational, not because the last layer provides you more information, but just because it's much easier to train. Otherwise, you can have a single layer with infinite neurons, and mathematically it's proved that it's a universal model that can fit any data, but it's difficult to train it. So that's why we use CNN or deep neural network or any structure to capture feature faster and easier. But the first layer, who is sitting next to the input, always is more informative about both your X and Y. That's what
you never use this, as far as I understand. Right? I think this is a good point that Shervin is making, perhaps. But this is
yeah, because I don't know about solving PDE with machine learning, but that's the only thing I know. So I just said that. Let me share it with you.
So a lot of convolutional neural network for classification tasks, right? The network setup is you have many convolutional layers in the start, and at the end of the convolutional layers, you end up with an image, and then you add a dense network which classifies for you, right?
Yes. I mean, you can have many different structure.
Right. Well, I mean, like, so that like what the kind of the architecture I said was,
and
like,
you know, people make this structure just out of thin of air. They don't have any scientific explanation why they are good. They just try and error, and then people come with the explanation why this could be useful. But as I said, the structure, the different neural structure, it just have faster way to extract your features and be trained, rather than providing you more information in the last layer. So I'm not. If you want a reference, do you know TCB work on studying discriminative model like this classifier by information bottleneck? That's one reference for this.
Daniel, you know this work because I mentioned Naftali.
You said, yes. Yes.
Yeah, use mutual information theory. We talked with Marcos the other day, I think, and yeah.
Right.
They know the work. Yeah. Any other questions? Thank you very much, Servin. Servin is a newcomer. Welcome, Servin. Any other questions for Dong or Daniel? Okay. Thank you, guys. Thank you very much. Maybe we can move on. Zogran, you can introduce the next speaker, but before that, let me say hi to Yannis Pandazis, who's joining us from my hometown, from Greece, from Heraklion.
Our second talk is given by Dr. Nat Trask. Dr. Trask is a senior member of technical staff at Sandia National Lab, where he is developing structure-preserving machine learning architectures for use in multi-scale modeling of problems in a wide range of applications, including shock physics, magnetohydrodynamics, energy storage combustion, material science, and etc. He's also a former member of our department. He was a PhD student in Plymouth here at Brown, and he graduated in 2015. So without further ado, let's welcome Dr. Nat Trask.
Thank you very much. I think I need to be given host sharing.
Yeah, you can share your screen now, I think.
It says host disabled participant screen sharing.
Oh, I already set you the co-host. Oh, no.
Doesn't look like it.
How about now?
Beautiful. Thank you.
No problem.
Just a second. I need to close my thing. Okay, here we go. You guys see my slides all right?
Yeah.
Yep, great. Okay. All right, so what I'm going to talk about is a new project that we started at Sandia about in September. So this is like a very recent work. We just finished the paper for this actually last night to submit to ICML. So everything I'm talking about here, there should be something on arXiv coming in about a week. Before I get started, I'm super excited to talk to the Crunch seminar. It was always my favorite thing when I was still at Brown, get pizza on Fridays and hang out. So what I'm going to talk about is really kind of like a higher level question about how can physics informed models be used to perform high throughput science. And so there's two big themes to this. The first one is multimodality, and I'll get into exactly what that means, but if you haven't heard that, that basically means heterogeneous data. Things like text plus images, plus video, plus audio, all at the same time. There's another big piece, which is physics informed machine learning. And if you're familiar with any of the work that we do in my group, that's actually most of what we work on. But I'm not going to cover that for this crowd because you guys, most of you already know all of the basics. And really the focus here is when you have a physics informed surrogate or data driven model, what do you do with it? But there are important details to this that I'm not going to get into, which is basically if you're going to use these kind of models in this way, there's certain like rigorous guarantees you need models to have, like that they're guaranteed to be stable and that they can perform out of distribution inference or extrapolation well. But the main goal that we're after is we want to discover exploitable information shared across these different kinds of data. And so I'm mostly focusing on this project on material science. And for material science with high throughput data, basically robots doing experiments, they make what they call big data, but for data science people, that's not big data. So they might make like 100 experiments or something like that, which isn't really big enough. So the tools, what I'm going to go over, which are called fingerprints that we're going to look for. These fingerprints are meant to facilitate this and give us actual access to really big data. So you'll see what I mean by that in a little bit. Okay, so in our group, and the same at Brown, probably at this point we have a whole inventory of like a million different kinds of problems in physics and this surrogate for that problem. We do a lot of stuff with solid mechanics. We do stuff with shock hydrodynamics, so things like shocks propagating through metals in extreme environments. subsurface flow, combustion. We're doing a lot of work with semiconductors. All of this work is basically has an eye toward forward simulation. Like you're going to discover a PDE, or maybe you're going to do some sort of inverse model, like you want to infer, like the previous talk, right? Like you want to infer a conductivity field or something like that. But really the question that we're starting to get interested in at Sandia is, sorry, a phone call. The question we're interested in is, now that you have these things, how do you actually do AI to do real science and engineering design? So not just say like, look, this surrogate can replace an expensive PDE solver, but do things that you could never do with a standard modeling and simulation kind of workflow or philosophy. What we're after is AI-enabled high-throughput material co-design. And so when I say high-throughput, there's kind of two ingredients to that. The first is high-throughput fabrication, right? So think about like lots of robots making lots of things all at the same time. And so we're looking at things like additive manufacturing, where you have custom parts, but now we've got robots that are going to make like 100 parts all in parallel, all in the same time, using automated processes. The second part to that is high throughput characterization, which is if you have a lot of parts, how can you rapidly do material characterization or experiment on these things, right? So on the top right here, this is something we use for mechanical testing. We 3D print a bunch of different types of specimens a robot can go through, and these are basically uniaxial tensile tests or you know, different deformations that you'll do to them. But a robot will come in and rip each one of these things apart very, very quickly and use that to calibrate a constitutive law, for example, for solid mechanics. So we're interested in fabricating lots of things, thin films, semiconductors. We're doing some work with lasers and silicon photonics. But all of these things fall under this classical thing in material science, this classical problem, where you get to control process properties, which is a high dimensional control space, like all the different knobs you get to twiddle while these machines are running. That predicts the structure, that governs the structure, like what's going on at the micro scale. But then the thing that you want to control at the end of the day is the property, like what is a target mechanical electromagnetic property, the conductivity or hardness or things like that. And so what we're trying to design is a like an AI framework to bridge those three gaps. So the tool that we're going to do is we're going to hunt for fingerprints, and fingerprint isn't a super well-defined thing in different fields. People call different things fingerprints. But in the abstract, it's basically an easily detectable signal correlating with some underlying, typically very complex physical process. So this is used all over the place, like in material science. This could be like feature engineering, a set of vectors, a vector of states which governs what's going on at a molecular level. And when people try and like learn molecular dynamics potentials from quantum DFT and things like that, they mean that sort of thing when they talk about a fingerprint. In climate science, this is actually how they do, how they detect and attribute climate change. So the state of the art for these kind of things, there's a lot of like doing PCA, you know, for climate, what they do is they just do PCA to detect an event, and then they do linear regression to detect whether that mode is active in a given data set, which is sort of classical and low tech from the perspective of deep learning. And the question that we have are, can we do this in a physics informed way, right? And this is a different version of physics informed than like what people do with pins, for example, or where you're trying to like build a PDE residual into a loss. Here we mean it in the sense of introducing an inductive bias into a fingerprint so that we can exploit the prior knowledge that we have about the physics that might govern a system. So I have a video here. This is a laser powder bed fusion machine. So basically what we have, this is one of the things we're working with in the project. So the way this thing works is it drags a bunch of powder, metal powder, and then a laser comes in and melts the powder, and layer by layer, you build things up in this way. So we use this for lots of kind of precision parts around the lab, and it's important because it lets you make things in this kind of bespoke way where you can make a custom part. The thing that is challenging about it is that it's very high variability. And so the engineering that we're doing at Sandia is very high consequence, and it needs to be perfect. And so there's lots of efforts all over the lab to try and improve additive manufacturing. If you take a look at this video, the process parameters are things that you get to tweak, like the laser intensity, the laser speed, like how quickly it's running back and forth, properties of the powder, like what's the size of the individual particles that make it up. And for these kind of data sets, you can do high fidelity characterization, right? You can do a very intensive experiment. You could get time on a synchrotron machine. You can do all these things to really like get into the microstructure. But there's also a lot of low fidelity signals coming off of this, right? So you can see just in this video that you have this light. You can see the plume coming off. That's this the ejecta coming off that you might be seeing. So there's light, there's sound, there's
this is real time? The video is real time or is accelerated time?
No, yeah, this is real time. This is just like a video, like a camcorder in the chamber.
Wow, fast.
Super fast. Yeah, and then, you know, and that's the thing about all of this stuff is that it's high throughput, and partially why we're so excited about it. Okay, so those different modalities, meaning like microscopy, X-ray images, light, sound, whatever, we're interpreting that to mean multimodality. And so multimodality is a little bit of a buzzword right now, just in the last year or so. So classically in computer vision contexts, this is what people mean when they say that. So take this picture on the left. There's this abstraction of a bird there. So a bird can be realized in different modalities, either through an image or through a sentence describing the bird. And those two modalities describe that abstraction in terms of complementary information. So what your brain is doing when it synthesizes, you know, all of your five senses, right? It's synthesizing all of those in such a way that it's more than the sum of its parts. Okay, so what's done in machine learning right now is really focused on text, video, and audio. So there are things like automated subtitling. You might, like in this Zoom meeting right now, I think you can turn on subtitles, right? That's a machine learned thing that's learned to sync up the audio that I'm saying with text. And that would be an example of multimodality. The challenge for these things is, as we all probably know, in machine learning, individual modalities have custom tailored architectures, right? So transformers are great for natural language processing, convolutional networks are great for image processing, and so on and so on. In order to handle these things all at once, what we need is a general purpose abstract framework that's modular. You can plug in different modalities, and it treats everything in a holistic way. There are some other success stories too. So people are using this in medical records and places like this. But again, this is what they have in mind is really wrestling with text. So for us, multimodality is different, and this is a maybe an unconventional interpretation of multimodality. So we have high fidelity material characterization, and these are the expensive things that you can do. So these are like expensive experiments. They might take hours to run, or direct numerical simulation, right? So it could either be physical or synthetic. And this high fidelity data, and it's great to follow up the last talk, right? Because this is the same focus on multi-fidelity. So this modality has all of the information, but it's time intensive. So you can't do this in a high throughput way. You can't have a robot executing these things, because eventually the scientist has to take the sample and walk it to the lab and then spend like 3 hours doing it. So who cares if you've got robots that can do all these little tests to it? There's this huge bottleneck stopping everything. On the other hand, we have low fidelity modalities. So these are like the extra bibs and bobs like all the little things that you can measure while this experiment or the fabrication is going on. So these things are typically just like completely thrown away and discarded. They're viewed as carrying little information, but they're trivial to measure. And if we could somehow get the best of both worlds, right, so that we could upgrade the low fidelity stuff so that it somehow had all of the information while still being trivial to measure, right, then we have a path to high throughput science. So last December, I was at this AI at DOE workshop, basically road mapping for the next 5 to 10 years what AI and ML will look like at DOE. And this multimodal scientific data was voted as the most important thing, along with things like causal inference, and of course, physics-informed machine learning. Okay, so here's an example of the kind of inference that we'd like to be able to do. I've got a bunch of lattices that we 3D printed, with different microstructures and so on. And we have a high throughput test, which actually, it's as high throughput as it can be. You're just squeezing these lattices down to generate a stress strain curve, right? So this is high throughput, but it's still pretty slow. This is like maybe 30 seconds per test or 10 seconds per test, but you have to load it up, do the test, right? So even with all of the acceleration in robotics, you can only do this so quickly. On the other hand, you can just take a picture of the lattice, right? And so these are two modalities that describe the same thing. You have this stress strain curve and you have these images. And these are the kind of tasks that you could try and do, right? Given an image, you might want to predict a stress strain curve. Given a stress strain curve, you might want to do generative modeling to prompt a picture of what the microstructure is that correlates with that stress strain curve to prompt hypothesis generation for people that want to do this is more of an explainability kind of thing. And then the thing that I'm really going to focus on is, can you look at both of these things at the same time? And so in this case, there's just two modalities, but the reality is for the experiments we're looking at, there's like 20 modalities. It's like every electrical signal coming off of an experiment, all of the audio, all of the video, all of that stuff. And so while a human might be able to wrestle with a few of these at once, right, really what we're after is an ability to sift through this in an automated way. So for this project, this is a figure from the proposal, which, at the time was more of a fiction and an abstraction of what we had to do rather than an actual thing. But this really defines like you can view it as like design requirements, right? So we have a given system. This is an electroplating system sketched out here. You have all of these different modalities, and given those modalities, we want to incorporate different kinds of machine learning, right? The black box kind of machine learning for like image processing, right? Like what physics informed stuff are you going to do there? But then also things like pins. If you have you might know a good PDE, but you don't know the material parameters, right? So pins are great for very quickly calibrating a low fidelity model like that. We have the other kind of work that we've been doing with structure preserving machine learning, where you have things that are like guaranteed to be stable and extrapolate well and things like that. So what we want to do is take all of these things in a way that you can produce a prediction of a property, right? So this thing spans this process to structure to property gap. And what we want to do in order to do this is learn these fingerprints, right? So these things that are going to let us encode all of that. Okay. All right, so that's the end of the hand waving. Now the rest of this, I'm going to get into the math and how we actually did this and put it together. There's some basic building blocks I'm going to go through as fast as I can. But this, I'm assuming that people do not have a background in variational inference. So this is like my whirlwind explanation of all of these ingredients that we need in order to make this work. And so the way to think about this is we're really building a system, not just like an individual, we're not working on like one network. This thing like folds in many different networks at the same time. So we've picked each one of these in some cases, they're not the best ones, but when you bring them together, we get very nice closed form expressions for everything. So that's something to keep in mind as we go forward. Okay, so first, if you haven't seen variational inference before, the idea is that you want to do Bayesian inference, right? You want to estimate a posterior distribution given a prior and a likelihood. And in order to estimate that distribution, you have to evaluate this term in the denominator here, which in general is computationally intractable. So there's broadly two sort of philosophies for how to wrestle with that. You can do sampling, but sampling is very expensive. And when you do sampling, that lets you do a one-time inference. And it's difficult to embed that as a sub-block within a system containing many different components that are trying to interact, right? So the other solution is you do variational inference, which gives you a nearby distribution, which, well, let me skip up here. We want to find a computationally tractable approximate posterior, right? So we want something which will give us closed form expressions, so we don't need to do sampling or anything like that. And once we have closed form expressions, then you have a module that you can couple to another module, is the way that we're thinking about this. So the way that this is typically done is you try and find this computationally tractable approximate posterior Q, which is as close as possible to the true posterior in the KL divergence. And so these equations here are just finessing this. This is just arithmetic, but you can rewrite this so that you get this expression down here. So that the probability, so the assumption here is that you have some hidden variables or latent variables Z, and then you have some observable variables X. And so you get this expression that says, and the assumption is that X is somehow generated by Z, right? So you have a generative model which says, given Z, then you can predict X conditioned on Z. Okay, so you get this decomposition if you rewrite this loss function that you're working with, and you get a KL divergence here, which is the thing that you actually want to minimize. And then you get this term here, which is called an elbow or an evidence-based lower bound. And so if you want to find the optimal distribution Q of Z, which is independent of X, minimizing the KL divergence is equivalent to maximizing the elbow, right? Because this term on the left-hand side is independent of Z. So that's our objective. We're going to maximize the elbow, which doesn't require any data on Z, whereas the KL divergence does. So in some sense, the elbow is integrating out the overall of the possible values of Z. Okay, so that's how we do these things. And so you're probably, I'm not even really going to bother to describe this stuff. I think everyone knows what an autoencoder is. An autoencoder is a tool for dimensionality reduction, for nonlinear dimensionality reduction, but it's purely deterministic, right? So you push something through an encoder and it maps it to a deterministic point in a latent space Z. And then you decode it, and you get this encoding and decoding just by minimizing a L2 loss or some other sort of regression problem. With variational inference, you can work with what's called a variational autoencoder, which does the exact same thing, but now it's set up as a variational inference problem. So you have an encoder which takes some high dimensional data and it maps it to a low dimensional latent space. But instead of mapping that to a deterministic point, it maps it, that point that it gets mapped to has a Gaussian distribution on it, right? So it's really mapping to random balls in the latent space is one way to think about it, is the way the probability is concentrated. And then for your decoder, you make an assumption of some sort of prior on how Z is distributed. And then you run that to a decoder to get your prediction. And so the elbow, the encoder is the posterior distribution, the decoder is the prior distribution, and the elbow is trying to make these two things match up in latent space. And so this is how it's typically done in a vanilla autoencoder. You know, you have you assume a standard unit normal prior. You learn a Gaussian distribution for the encoder, and then you plug these into your elbow, and it decomposes interestingly into this sort of regression loss, like a vanilla autoencoder, no variational anything, right? Like the one in this slide, that you get the same loss term here. And then you get a regularizing term, which penalizes the mismatch between the prior and the posterior. So the thing that's a little bit magical about this is that there's a closed form expression for all of these terms. So you minimize this the exact same way you minimize an L2 loss, right? You just throw gradient descent at this thing. That's what's attractive about it. Okay, so vanilla autoencoder versus a VAE, the prior, right, you assume it's a unit Gaussian, it gives a better distribution of data in your latent space, right? So this is an MNIST example. Each one of these colors corresponds to a different digit. And you can see that the digits are clustering in the latent space, but there's some overlap. That, you know, this might be a 2 or it might be a 3, who knows? They're all getting mapped on top of each other in the latent space. So what the VAE is doing is it's promoting regularity, right? Because you can't overfit to data in the latent space. Everything in that random ball has to look roughly the same in the encoding. You get some better clusters, you get less overlap, still not great, but it's a step in the right direction. And so the way people use these is you can use them to do generative modeling. So now if you sample from the distribution that you've learned, right, meaning you choose a point in this latent space Z and you decode it, it'll generate a picture of an image. And it's not an image that existed previously. It's something from the distribution of samples that you trained on. So this is nice, but for a long time, nobody did much with this. The attractive thing is that it's unsupervised, meaning you don't need expensive human in the loop labeling, which we care about for high throughput. So then people started looking into this idea of disentanglement. So if you start playing with that regularizing term and you either dial it up or down, this is called beta VAE, you get your clusters in latent space, they start to disentangle, right? So now all of your 2s are separated out from all of the other ones. And so this paper was a pretty huge paper at the time. Once you have these disentangled clusters, DeepMind realized that they lend themselves to interpretability in each cluster, and you can use them to do generative modeling, right? Like if you sample from the orange cluster, that'll correspond to a specific unsupervised, detected in an unsupervised way, interpretable feature of your data set. So you might have seen these pictures where you got a bunch of faces, but then you can dial a mustache into the face or dial it down. More recently, people have started working with disentangled representations where you have a Gaussian mixture prior. And so the idea here is you assume that things aren't a unit Gaussian in the latent space, but you're learning a mixture of Gaussians, right? So this is a little bit subtle, but this gives you an explicit parameterization of the clusters. So with beta VAE, yeah, the data gets mapped into a cluster, but you can't say, give me cluster 1, give me cluster 2, and then do some downstream task with it. For this, you have a individual Gaussian distribution for each component of that mixture. And if you sample from each one of these components of the mixtures, they have interpretable features as you sample in different directions, right? So each cluster, this is sampling the mean of each thing for MNIST, right? And you can see, oh, this is the cluster of 5s, this is a cluster of 6s, the clusters of 0s. And then if you go into the 0 cluster and you sample, I think this is across a couple standard deviations within that cluster, you get different kinds of 0s, and it reveals features that are encoded by that cluster. I'm gonna skip that part. This is the paper. This should be on archive. We go through each one of these things and talk about how to do it, but really we're trying to like combine all of these things all at once. So this is the architecture that we've put together. It's called PIMA, for Physics Informed Multimodal Autoencoder. And I'll get into the math now, which is a little bit low level. But before I do that, I just want to give like kind of the big picture to orient everybody. So the way this is organized is you have all of your different modalities. We call these X1 through XD for the different kind of modalities. Some of those modalities are black box data, things like images. Some of them are what we call scientific data, something that we know how to model, like from first principles. So each one of these things through this, variational inference kind of framework gets encoded into a normal distribution in the latent space. And then we apply what's called a product of expert strategy to combine all of these things. And I'll get into the details later, but what it boils down to is that the product of Gaussian distributions gives you another Gaussian distribution. And Gaussian distributions admit closed form expressions. So by performing, we call this modal fusion, by combining all of the individual modalities and folding them into one Gaussian thing, which we call the multimodal distribution, we've fused all of them into a common posterior distribution that spans all of the modalities. The right-hand side, this is the generative model, right? And we have this Gaussian mixture model. And so the thing that's really nice about this is that this will give, we'll get there in a few slides, but this will give a closed form expression for the elbow. So we've picked each one of these individual things so that we preserve that property. So now that you have your embedding in latent space, you want to push it through the decoder, right? For the black box data, you can just use a standard decoder, right? We use convolutional autoencoders for the encoder and decoder for those guys. But for the scientific data, and this is the most important part of this entire thing. If you remember one thing, it's to look at this tan box. This is our subject matter expert model, or our physics expert model. And this is a parameterized model, which will describe that data. So I'll get into some examples for what this could be. But for example, we're talking about stress strain curves. A very simple expert model is that we assume a linear strain hardening law, right? Just this bilinear form. And we assume that that will fit the data, right? So there's a lot of, even in something as simple as that, there's a ton of physics, right? That in a very interpretable way describes the yield stress, the elastic modulus, the plastic modulus. And so now we're forcing our decoder, we're forcing our embedding to find something that decodes into this interpretable physics-based model. And where we'll go with this is that there could be, especially with this crowd, you should think of a physics-informed neural network here. That is, think of a depot net, think of all those kind of things. Okay, so
Nat, I just want to make a point that this really framework is ideal for biomedical modeling.
Yep.
We have a project like that, we have mice data and so on, but that sort of multimodality, it has exactly what you show here. It has strain curves, it has histology measurements, it has all this stuff. And I think that's really big for medicine. And I like the synthesis of all these ideas. Of course, also the variational encoders with the uncertain quantification. But what I'm saying here is this is not just PIMA, it's also medicine, and it's lots of other things, but medicine right here.
Yeah, we argued about whether we should do knowledge informed or physics informed.
No, it's good for this, for Sandia, but I'm saying it's really, it's a great conceptual framework which has a direct implementation, like with the components that you put there. So,
yeah, exactly. And I put this together as a requirement because I'm part of this project which synthesizes multimodal data. So we put it together, and I was initially just targeting all this material science stuff. Since it's been working across the lab in there's just a ton of problems that have this multimodal plus expert model pattern to it. So it's actually, I'm talking a lot about materials, but this maps pretty broadly. So before I
excuse me, I have a question here. So I think you make a very strong assumption in the latent space. When you take the product of Gaussian distributions, it means that these latent variables for each one of these encoders are independent from the others, and they're not. Right?
Yeah, for sure.
So so there are correlations there between the data that come, from the gray thing there on the top and the other thing. In other words, multimodal data, the whole point of it is that there are correlations between them, right? And that's what you're trying to uncover. But when you make this assumption of a product of Gaussian distributions in latent space, it's as if you are ignoring completely all the correlations.
Yes, absolutely. And that was something that stressed me out for a very long time. I've been talking to a lot of people who do a lot of Bayesian modeling. And the thing that I had to let go, given my personal probability training, is that you're used to trying to build a model with appropriate models for dependence, right? Like when people use copulas and things like, like you're used to trying to put something together like that. My understanding, my limited understanding, I'm not a probabilist, I'm a PDE person, but my limited understanding is that for variational inference, like people use much worse approximate posteriors. You make it accurate by solving the optimization problem to make it match the true posterior as close as possible.
But there is also a way to actually start including the dependencies by using in probability, if you have the joint probability of certain random variables, right? If they're independent, then the joint probability just becomes the product. But if they're dependent, you can still write the joint probability as a product of conditional probabilities. So all I'm saying is that you can start, let's say, from encoder, the top one that you have with mu1 and sigma1, you can start as this as your starting point, and then you can build an encoder, for the second modality, which is conditioned on the first one, and then for the third modality, which is conditioned on the first two. So you can have this product structure, but it will be about conditional probabilities.
I agree. Space. Yeah, we talk about this in the paper. There's a lot, that is a second school of thought in this multimodal thing, like whether you want to work with a joint product distribution or you want to build up like the dependency.
Panos, then you lose all the, of course, you're right, you're more rigorous, but you lose the analyticity, right? You're not going to have closed form solutions for Zogren, I think Zogren...
conditional probabilities could still be, yes, they could still be Gaussian, I think. If you take a, yes, it could be.
I think the problem is with the variational inference. I think Zogren in the paper we have some things like that, right? In the long paper.
Yes. So, but we do it in the assumption for the parameters are different. So here, Nat assumes that we have the Gaussian random variables to be the latest data variables, but in the UQ review paper, I think we assume the parameter from the network parameters. So those are different, but the method is the same.
Yeah.
Nat, can I ask a question?
Sure.
What is now? How many modalities do you have here for this model?
For this example, there's 2 as drawn.
And what is the dimensionality of mu1 and mu2?
That is a hyperparameter that you get to choose the same as any autoencoder. We've done, I think I have a slide showing the study that we did exploring that. So it's different from the usual autoencoders. It's really just, there's some dynamics that I'll show during training. Let me answer that question in a few slides when I have some videos up. Because what matters is how the clusters, the dynamics of how the clusters evolve within the latent space.
So if the dimensionality says you only have 2 modalities, and if the dimensionalities of mu1 and mu2 are not that high, I think you can combine them into one Gaussian, multivariate Gaussian. So for which you don't have to deal with this independence between two modalities.
Yeah. There's like there's like, you know, people have been working on this just a few years. There's dozens of papers of alternate ways of combining things for the encoding side. Like George mentioned, what we wanted was something simple and which preserved the analytic expression for the elbow. But you know, tons of different, you know, I kind of just picked something and then I didn't want to think about it anymore because it's a little bit paralyzing to choose the very best encoder. Just like all network design, you know?
Yeah,
yeah. So let me move on from this slide and get into the actual math, which I haven't brought up yet. But the thing I want to point out is that these clusters are what we are calling fingerprints. And this is how it works. So you can do, you can do cross-modal inference, right? From a single modality, you can encode into latent space. You can identify the cluster associated from that. And then you can decode in either direction to do generative modeling to predict the other modalities, right? So one thing is, yeah, this gives good clusters and you can use those good clusters for downstream tasks. But the important thing is now you've learned, like, call it a Rosetta Stone. You know, it's like a thing to just translate from expensive or from cheap experiment to expensive experiment. And so all of that junk I was saying at the beginning about where we want to go with this is the important thing about how we're interested in using it. The other thing I should point out that's maybe obvious for this crowd, but this gives uncertainty estimates, right? You can say, given this data, what is the probability that it belongs to C? You can evaluate the Bayesian posterior, like the probability of C given Xi, and you just get a discrete probability distribution. So that is very attractive in scientific settings in terms of quantifying some notion of certainty about whether this fingerprint tells you anything, or maybe it's just, you know, there's no information in it. Okay, I'm going to go into the details now. There's a lot of math. I'm going to try and go through it pretty quickly. Let's see how many slides I have. Yeah, I'm going to try and go through it quickly. These are the ingredients. We need to work through the unimodal embeddings, this product of experts idea, how to do this Gaussian mixture prior, how do you do the expert physics model, and so on. Okay, so this is the elbow that we want to maximize. We make this mean field approximation to break everything up. This is kind of along the lines of what Panos was saying, right? If you assume this multiplicative structure, right, then the log of all these products is going to give you a bunch of sum of exponential of log of something that you have to compute. And so that's once we make this assumption so that you get these sum of nice individual terms to integrate. This is where this product of experts thing comes in. We want to preserve this product structure in the same way for the posterior distribution Q. This is the formal derivation. This is what Panos was talking about. You have to assume, you know, basically the way you derive this expression. This is an identity here. If you apply Bayes' theorem to this expression, and then you assume pairwise independence of x1 condition, or sorry, z conditioned on xi and z conditioned on xj, that those are pairwise independent. So what we do, which you're allowed to do in variational inference, because you're just guessing some model form to fit. It's just an ansatz, right? It doesn't have to be, it could be any distribution at all that you want to fit with the elbow. So we just drop this term here, and then we're left with this. In the literature, people use this as a way to put different priors on your latent distribution. So what we're doing, you could view as putting an uninformative prior on the distribution of data in the latent space. And this is a closed form expression. This graph probably everyone knows. The product of Gaussian PDFs is a Gaussian PDF. This is a Gaussian mixture prior. You assume that the class labels are categorical. In TensorFlow, when we do this, we have a trainable vector pi that we feed into a softmax, right? So now you have something that you can do gradient descent on that parameterizes the categorical distribution. We're learning for each cluster a mean and a standard deviation. We assume that those are uncorrelated in the latent space. This is done throughout the literature, but this is what makes you get different features in different directions, right? This is Z1 and Z2. So by assuming that they are independent, it kind of forces it to vary in different ways in each direction. I'm not sure whether I actually believe that. That's like the folklore. Let me preface it by saying that. Okay, so now that you have the clusters, this is how you do the decoding, right? So you predict the modalities by conditioning off of the cluster. And what the distribution that we're going to assume is that the mean is given by some nonlinear regressor, right? So this could be as simple as like a generalized linear model. And that's how mixtures of experts were originally done when Michael Jordan did them in the early 90s. He was just doing generalized linear experts. But we're going to use this in a very, very different way, where this is where we inject our physics information. So by choosing this judiciously, we are asking for a physics-informed autoencoding. So the nice thing about this is that, again, this has nice closed form expressions. So you can predict expectation, the variance for the predicted modalities at the end of the day. I'm not going to actually go through this, but like I said, right, because you have that product structure, the log of the product gives you a bunch of sums of individual terms, right? This thing, this thing, this thing, this thing, and so on. All of these things have closed form expressions, except for this one. The categorical, I might lose a lot of people here in the weeds, but in order to do variational autoencoders, you have to do what's called the reparameterization trick, so that you can backpropagate through a random node. There is no backpropagation, or there's no reparameterization trick for a categorical distribution. So you're forced to treat this in a nice way. And so you can derive an estimator that we do like so, right? So you can rewrite the elbow in this way. And when you rewrite the elbow in this way, and then you see that the minimizer with respect to Q of C conditioned on the unimodal inputs has this term here, right? So if you estimate this distribution as the probability of C conditioned on Z, then that minimizes this thing, because this term here is independent of C. So there's a little bit of a trick here. There's a clever estimator that we pulled from a paper. I'm not going to go through these, but just believe me, these are all of the closed form integrals that you need in order to evaluate those things. They give you these nice looking expressions that are just functions of the model parameters. And then this distribution here, which is another thing with the closed form estimate, is the Bayesian posterior to identify what cluster you're in. Okay, there's a lot. The important thing is it gives you this elbow. So you go into TensorFlow, you code this thing up, then you just throw atom at it. The thing that is really slick about this, that I'm really, really excited about, is that there's a type of training called expectation maximization, where you hold the posterior estimate, which in this case is this thing. You hold that constant, and then you optimize the remaining parameters. So it's a lot like a block coordinate descent kind of strategy, right? Like you freeze some variables, optimize the rest. And if any of you have seen our like least squares gradient descent paper, we use this idea a lot in different things. And so magic formulas pop out. You get a closed form estimator for the clusters. So each step of training, you don't do gradient descent on the cluster centers. You just evaluate this formula. The most important thing is that you get one of these for the expert model. So at each step of training, you can solve, it's just a weighted least squares problem, right? This is a little L2 weighted by the posterior distribution. You get this problem for the parameters in your expert model, which means, so if you think about it, we've got like 20 things we're trying to train simultaneously, but we can make sure that some of these things are moving along a manifold of the optimal fit to some subset of the parameters. So that's super exciting. Okay, that's all the math. Now I'm gonna check the time. I have experiments to walk through that shows how this works. I'll probably skip the applications at the end. So the first application that I'm going to show is totally physics agnostic. It's completely meaningless and it's a toy problem. It's just pedagogical. So don't, some people don't like this. Don't get too worked up about it. It's just a super concrete way to dig into this. So imagine you have some latent variable z, which is a digit. And then we have two modalities corresponding to those two things. One is an image of that digit. And then the second modality is a 1D function whose slope corresponds to that digit, right? So you might have a, oh, one sec, where'd my pencil go? Here we go. One item of data would look like these pairs, one image and then one function whose slope is 9 plus some noise. This is a toy thing, but what we want to do is we want to train this in an unsupervised way, right? So we don't give it any data on Z, and we're going to use an expert model where we assume x2 is just some constant times x. Right? So we're just going to fit a linear expert model to this. And so if you think about it a little bit, you'll realize that this is really not that far from supervised learning, right? We're just dressing up the label and, we're encoding the label as the slope of another modality, right? So this isn't meant to be mind-blowing. This is meant to show the dynamics in a situation where it's very clear what kind of information is shared across modalities. Okay, here's some videos of it training. So over the course of training, you can see the clusters just untangling. You can see the expert models fitting to each cluster. These images show the decoded means of each cluster over the course of training. At the end, you're left with 5 functions that go through the different subpopulations of the data. They have a probability distribution on them that tells you how well they fit each subpopulation. You have a generative model for each picture. This is in the top right. This is what you would get doing the same sort of thing with a traditional variational autoencoder. These are the clusters that we get. And so if you do classification, so there's classification accuracy for unsupervised learning is just you look at the mode of a given cluster and you associate the label which occurs most often in that thing, right? So we don't know, like we just get a pile of clusters. We don't know which one is a 2 or a 3. But if we look at the labels that were held out during training, we can say, oh, this is a 2 after the fact. And 99% of the things in this cluster are all 2s, right? For this case, we get 100% classification accuracy. So it completely disentangles. That shouldn't be surprising because we're augmenting MNIST with this extremely informative second modality of data. But even state of the art for supervised classification for MNIST is like 99 point something %. Right? So in this case, it's actually really perfect. So these are some comparisons to the state of the art. We do this with adding a little bit of noise to the curves or a lot of noise, right? So I think it's either 1% or 50%. I don't have the exact number for how much noise it was. And you can see what happens if you're doing multimodal inference for clean versus noisy. For clean data, it's 100% accuracy. It drops down to 98. For the cross-modal stuff, it's still, in some settings it works, in some settings it doesn't work. It's a long story to get into when and how careful you should be about doing cross-modal inference. But the thing that is most exciting is how it's actually doing the embedding in the latent space. So this is the clean and the noisy data set at the top and the bottom. If you look at the clusters, it's ordering the clusters in the latent space, which nothing does, right? So you have a 0 next to a 1, next to a 2, 3, 4, 5, 6, 7, 8, 9. And so the ordering in X2 is reflected in the embedding for Z, which is very important for generative modeling. It means if you sample from, say you have an image and it can't tell if this is a 3 or what it is, right? But the second modality tells you, well, the 3 is somewhere in between a 2 and a 4. And now your generative model, even if it's getting things wrong, it's steering it towards the bias imposed by the second modality. Hopefully, it's kind of a, I don't quite have the words for how to explain this, but there's something really exciting here in terms of how this combines information. And so as you add more noise, essentially making the second modality less informative, these clusters start to bleed into each other, but you still preserve roughly this this relationship from cluster to cluster, right? This is roughly going from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you look at the generative modeling, this is what I mean, right? So let's look at something like 2, right? In the center of the cluster, it knows for sure how to generate a 2. As you go out to the edge of the cluster, where it's not sure whether it's a 2 or not, it does get confused, but it gets confused by nearby data, right? It says, oh, I might make an error and predict the wrong image, but it's a 3. It's something that's close to a 2. And you can think about what that, and it's the same story as you look across all of these things. So you should think about what that means for in a physics setting, right? It says, I might not get the right microstructure, but I'll get a microstructure that's at least close to one with a similar stress strain curve, right? This is, that sort of hypothesis is corroborated if you look at the confusion matrices, right? These show what class pops up how often in each cluster. The top is the clean, the bottom is the noisy. From left to right, this is all of the modalities at once, just from the images, just from the curves. And you can see that for some things, right? So for example, when the curves are noisy, it doesn't do a good job because the noise is big enough that it could just as easily be close to a slope 2 or a slope 3. It's too noisy to tell, but it's banded. They're all banded. So it's only making mistakes in a way that it's making mistakes in a localized way. Hopefully that's clear. Maybe it is, maybe it's not. Let me show a video of this stuff actually working. So these are these compression tests I was talking about. We 3D printed a bunch of these lattices, we compress them, get a bunch of stress strain curves. There's 2 different populations of lattices corresponding to these, call them a gyroid and an octet lattice. The name isn't super important, it's just that there are different patterns that are being printed here, and that they break into these roughly 2 populations of stress strain curves, but you can see that it's ambiguous, right? Some of these blue lines, the stress strain curves could come from either one of those populations, right? So just from the stress strain curve, you could not infer if it was lattice 1 or lattice 2. So let's look at how this trains. And if you look, so there's 2 clusters, you can see over the course of training, they're swapping points back and forth from one cluster to the other cluster. Eventually it gets good clusters. You can see how the mean, because we're using the expectation maximization that gives a closed form expression for the mean at each step. The mean is always tracking the cluster. It's not like you have to wait for the mean to catch up. once you have good clustering, you get good generative images. Once you get good generative images, you can see that it knows how to fit. Now it's pieced apart the two things, and it can fit the stress strain curves to both cluster. And so now we can use this. We can use this. We can just take a picture of this and get the same sort of information that you would get out of a stress strain curve. I don't know. I have some directions. I'll just blow through this. We're looking at doing stuff like taking audio while like putting a microphone in the laser powder bed fusion chamber and trying to get an audio signal that matches images. We have these experiments where you do scratch tests. It's kind of like dragging the needle on a record player across a thin film and trying to gouge out some material. That tells you properties about hardness, delamination, all these kind of important things when you're designing a thin film, right? And so we have images of these modalities, but we also have all of these like low fidelity things that come off of the machine, so that we would hope we don't need to do all this time intensive imaging. You could do things like go in to an expert model and you can do much more fancy physics informed circuits. Maybe I'll just leave it that way. So I'll stop here and take questions. The thing, the main punchline is that multimodality is super, super important and exploitable, and especially in science, like more so in science than in the way people are doing it right now in black box machine learning. And for this stuff, we've just been talking about clustering and this cross-modal inference, but you can use this in lots of other ways too. You could use this to do causal machine learning or anomaly detection or active learning and so on. So yeah, maybe I'll stop here.
This is amazing. I hope you patented this.
Yeah,
I'm serious.
I think
there's lots of technologies here. There's a lot. I mean, it's easy to patent this really in many different. But that's amazing for solving real problems. So I thoroughly enjoy the presentation.
Thank you.
Do we have any question for Nat? All right. If not, thank you, Nat, for this talk.
Hold on a second.
I had a question. This is Varun from
yes, Varun.
170. Dr. Trask, could you go to slide 37 where you are showing your predicted stress strain curve?
37, 27.
Where you're showing your prediction of stress strain curve from
this one?
Yes, this one. When you actually run it through to the end.
Mm-hmm.
You see a small corner at the end, like where you have a corner at the where the linear stress is actually changing to plastic stress and all that. Is there a reason for that corner to exist?
Yeah, so the expert model that we've chosen here is a linear strain hardening model.
Yeah.
A linear strain hardening model is something that's piecewise linear like this, right? So we assume that we can fit this data with something that, these are degrees of freedom. We choose, it has to go through the origin. We need to fit this point where the elbow occurs, right? So there's 2 degrees of freedom there for the X and Y coordinate, and a 3rd degree of freedom for what the slope is once it's in the plastic regime, right? So this is a nonlinear 3-parameter model, but it encodes this transition from elastic to plastic response.
Okay, thank you.
Maybe Enrui has some questions. Enrui.
Yeah. Let me see. I don't have any question for now, but I think this work is really amazing, and essentially there are lots of applications not only in this type of engineering but also other like biomedical, where we have lots of different modalities from experimental measurements which give different forms of information regarding the genotype or phenotype of any biomedical system.
Andrew just wrote a paper where he goes from stress strains and biaxial testing to genotypes. We call it G to phi, the Greek phi for phenotype.
Oh, really? So you're trying to get you're trying to correlate biomarkers with a mechanical test on
the mechanical test give you which genotype comes from. So we have 5 different mice. So you only use one type, but we could use multiple, because that's what you demonstrate here. Multiple modalities work synergistically, and that's what the example with the noise you show that how you can actually cluster. And he had 85% classification accuracy, but I think he can go higher with.
Yeah, but we could get higher. Let me say that, to Andrew and to everyone, basically, the beautiful thing about machine learning, this is just like a little Python script that encodes all of this. I mean, there's a lot to get it to actually run on a big cluster and train quickly and stuff like that. But it is so unbelievably easy to just apply this from one data set to another data set. The only thing we need to do is choose the expert model. So if anyone has multimodal things, I would be very happy to collaborate and to take a spin on your data if you want to write an easy paper.
And the whole, I mean, I think Ishan is also listening, and we had this data. We can have, imaging data, we have metabolomics, genomics, and so on, all this data, and then you have other. That's why I said medicine is the big playground, actually, for, and there we use also models, expert models, single view, multi-view. All these are sort of common things that we are also trying to introduce. Any other questions for?
I should make this comment too. You can input, maybe this is obvious, maybe not. You can input synthetic data as an extra modality, right? So you can run DNS, and you can ask your DNS to inform whatever your stress strain experiment was, right?
That's right. Yeah. So and you can see how you can
all these things that are usually like different pieces.
Work for closures as well, and lots of different applications. Any other questions for Nat? Maybe you can show your paper, Nat, the archive paper, so people can write it down, because I think there's a fair amount of interest, certainly from multiple people in my group, but I think others too. Yeah. So that's in the archive, right? You don't have the archive number, but that's okay.
No, it's in review. It'll be on the archive next week.
Okay. Yeah, thank you very much. Before Zogren, before you close, I want to wish all our Chinese friends around the world happy Tiger Year, Hunyan Kuai Le. Why don't you close the session? Thanks, Nat, again.
Yep, take care.
Thank you.
Bye,
no, George, we have another session for today. So this is for Crunch member only. So for all the other people, you may leave now. Thank you for attending this week's seminar.